Today we look at chemical disinfection, and in particular at chlorine, which is the most widely used disinfectant globally. We'll explore a bit the chemistry of chlorine and chlorine dosing. We'll look at different forms of chlorine, gas, liquid, and solid, and review the effectiveness of chlorine in reducing pathogens. Finally, we will give an example of chlorine use in Haiti. Chlorine has been used for over a century in the treatment of drinking water, beginning in the UK and the USA in the early 20th century. Today, chlorine is used in 98% of U.S. water utilities and in similarly high numbers across the world. Chlorine is also widely used at the household level. Of course, many households use bleach for cleaning and laundry, but in surveys conducted in low and medium income countries, 5.6% of respondents reported adding chlorine to their drinking water to make it safer to drink. This was the second most common household water treatment practice mentioned after boiling, and was particularly high in Latin America and Caribbean countries. Chlorine is a strong oxidant, and it reacts rapidly with different kinds of organic material, including cell walls, DNA, and enzymes. That's also why it's good at cleaning things. It really destroys organic compounds. But actually, in part because it's so reactive, the key mechanisms in pathogen inactivation are not well understood, especially for viruses and protozoa. When we talk about chlorine, we can refer to many different things. Large drinking water utilities typically use elemental chlorine, present as chlorine gas, which is cost-effective and includes, by definition, 100% chlorine. The next most concentrated form, also used in many utilities, is high-test hypochlorite, or HTH, which contains about 60 to 70% chlorine and comes in powders or tablets. Bleaching powder, or chlorinated lime, or calcium hypochlorite, is another powdered form and is often marketed as around 35% chlorine, but the chlorine isn't stable and actual concentrations vary widely, sometimes as low as 15%. It makes calculating doses difficult. Household bleach is a solution of sodium hypochlorite, usually around 5% chlorine, and Javel water is a similar product, typically a little bit less strong. Finally, it's possible to make chlorine locally by passing an electrical current through simple salt solution. This usually results in something less than 1% chlorine. Whatever the chlorine source, when it is added to water, it becomes hypochlorous acid, or HOCl. And hypochlorous acid loses a proton at higher pH and becomes hypochlorite, or OCl, with a negative charge. These two species together are called free chlorine. At pH 7.54, the two species are present in equal amount. At higher pH, hypochlorite dominates, while at lower pH, hypochlorous acid is the main species. This is important because hypochlorous acid, the one with the proton attached, is a much stronger disinfectant than hypochlorite. For this reason, it's recommended that water should always have a pH of less than 8 when chlorination is being applied, so that there's a reasonable amount of hypochlorous acid present. Chlorine is highly reactive, and when added to water, a lot of the chlorine will react with natural chemicals in the water. So the dose has to be big enough to meet both the chlorine demand of the water and to produce a residual that is strong enough to kill the target pathogens. Chlorine demand can be caused by organic carbon, which is naturally present in surface waters, but also by iron and manganese or ammonia, which tend to be more present in groundwater. It's normally recommended to have a residual concentration of at least 0.5 milligrams per liter, and this can require a dose of anywhere from 1 to 5 milligrams per liter, with 2 milligrams per liter being fairly typical. Turbidity reduces the effectiveness of chlorine, both by shielding pathogens directly and by consuming chlorine, so standard doses are normally doubled when the water is turbid. Ideally, The right dose will be determined through trial and error by adding different amounts of chlorine to the water to be treated to see what yields the desired residual. Chlorine doesn't pose any health risks itself, though the concentrated forms can be dangerous to handle. WHO does list a guideline value of 5 milligrams per liter, but this is conservative and would probably result in unacceptable tastes or odors at this level in any case. The use of chlorine in household water treatment was first developed by the U.S. Centers for Disease Control and the Pan American Health Organization. They proposed an intervention including 3 elements: chlorine disinfection, and this was later expanded to include other HWTS processes, safe storage, and behavior change communication. This model has been widely taken up, especially through Latin America and parts of Africa, and typically involves production of a dilute sodium hypochlorite solution around 0.75% free chlorine. Now, because hypochlorous acid is much more reactive and also more volatile than hypochlorite, the shelf life is much longer at high pH, so these solutions are typically stabilized at pH 11 or greater. For similar reasons, household bleach has a pH of around 12 and is slightly irritating to the skin. In different countries, different brands of liquid chlorine are promoted. Some of the common brand names are WaterGuard, Chlorine, Claro, and in Francophone countries, Sureau. The bottles are normally designed so that 1 capful is a good dose for the locally used storage containers. For example, a 5 milliliter capful of 0.75% free chlorine added to a 20-liter jerry can gives a dose of 1.9 milligrams per liter. And again, this dose should be doubled if the raw water is turbid. There is another form of chlorine which isn't used in conventional water treatment, but is popular in swimming pools and increasingly in household water treatment. This is a chemical with a long name. It's called sodium dichloroisocyanurate, so you can see why people call it NaDCC instead. And it's about 60% free chlorine by weight. The other 40% is a chemical, cyanuric acid, which bonds with free chlorine and provides a reservoir. Thus, as free chlorine is consumed through chlorine demand or inactivation of pathogens, the reservoir can release more free chlorine into the water. Cyanuric acid itself doesn't pose a health risk. The guideline value of 40 milligrams per liter is well above levels that would be reached in drinking water treatment. Because of this reservoir effect, NaDCC allows a more steady and consistent free chlorine level, which may lead to fewer reports of taste and odor problems. NaDCC is produced in the form of effervescent tablets, or fizzy tablets, which are individually wrapped and have a long shelf life. They come in a wide range of concentrations. The most popular are 33 and 67 milligram versions, which are good for 10 or 20 liters of water, respectively. Aquatabs, shown here, is one of the leading brands globally, but there are others as well. NaDCC tablets are easy to use and have proven particularly popular in emergency settings, but now are increasingly used routinely at the household level. Chlorine efficacy, like other disinfectants, is a combination of the concentration and the time of exposure. For chlorine, the dose can be expressed as a CT value in units of minute milligrams per liter. For conventional drinking water treatment, a common goal is to have a residual of 0.5 milligrams per liter free chlorine in contact with water for at least 30 minutes to ensure a good pathogen kill. Multiplying these together gives a CT value of 15 minute milligrams per liter, which is also equivalent to 15 minutes at 1 milligram per liter. In HWTS, a typical dose is around 1.9 milligrams per liter, which gives a larger CT of 56 minute milligrams per liter. How effective is this dose? Well, this chart shows the CT99. That's the CT dose necessary to achieve 99% kill, and you all know instantly by now that that means a 2 log reduction value, right? Well, bacteria are very sensitive to chlorine, and a CT of less than 0.08 is necessary to achieve 2 LRV. But viruses are significantly tougher. It takes a CT of from 2 to 30 to get our 2 log reductions. And protozoa are tougher still, with CT99s from 25 to 245. And that doesn't include cryptosporidium cysts, which are basically unaffected by chlorine. One study even reported a CT value of over 15,000 just to achieve 3 log reductions of cryptosporidium. Now recall, our typical dose was in the range of 15 to maybe 60 minute milligrams per liter, so you can see that chlorine is not very effective against some protozoa. Now, to be fair, not all protozoa are as resistant as cryptosporidium. Giardia, for example, has a CT99 of about 15. So on balance, chlorine can achieve from 2 to 5 LRV for protozoa, though not for cryptosporidium. Bacteria are more sensitive to chlorine, and removal can easily exceed 6 LRV. Viruses have intermediate resistance. Disinfection might take a bit longer, but still good removal can be achieved. Up to now, we've been talking about free chlorine, which is that combination of hypochlorous acid and hypochlorite. But when free chlorine reacts with ammonia, it creates a different form called chloramines, and there's a whole family of chloramines with monochloramine, dichloramine, and trichloramine. These are called combined chlorine, and they're a less efficient disinfectant, but they're still used in some countries because they are long-lasting and can be useful, say, in a distribution network. However, the chloramines have a stronger odor, especially trichloramine. In fact, trichloramine and a bit of dichloramine is what's responsible for that swimming pool odor if you've ever smelled a strong indoor swimming pool. It's not the bleach itself or the hypochlorite, it's the combined chlorine. Combined chlorine isn't typically used in household water treatment, though it can be formed unintentionally if the water has high ammonia levels. There's another important potential unintended reaction that can happen with free chlorine if there are high levels of dissolved organic carbon in the water being treated. Then the free chlorine will react with the carbon and produce what are called disinfection byproducts, such as trihalomethanes or haloacetic acids. And some of these compounds have been shown in laboratory studies to cause cancer in laboratory animals when applied at high doses. So accordingly, WHO and many governments have derived health-based drinking water guideline values for these compounds in drinking water. And these are typically set at a level which would be expected to cause 1 additional case of bladder or kidney cancer for every 100,000 people who drink 2 liters of water per day at that guideline value for a 70-year lifetime period. And while that is a real health risk, it's still very small compared to the mortality rates caused by diarrhea and other waterborne diseases. Here's what the World Health Organization has to say about disinfection byproducts. The Jolivet Safe Water for Families program has sold sodium hypochlorite to households in rural Haiti since 2002. The program began at the Missions of Love Health Clinic in Jolivet, northern Haiti, and since 2008 has been managed by the NGO Deep Springs International. The program makes its own chlorine through electrolysis of salt water, which is branded as Gadyen Dlo, meaning water guardian in Haitian Creole. Project team members enroll families by selling safe storage containers, or boquete especial, with lids and taps. The team also sells bottles of Gadyen Dlo, keeping sales records for each family and conducts regular household visits to monitor use and provide ongoing education. One bottle costs about $1.25 and contains enough chlorine to treat an average family's drinking water for about a month and a half. By May 2010, the program had reached over 4,000 participants and had sold enough Gadyen Dlo to treat 12 million liters of drinking water. In 2010, an impact evaluation was done in northern Haiti and reported a few years later in a scientific journal. The team found that 3/4 of the randomly selected households in the program area reported that they were currently using Gadyen Dlo, and 56% of these households, compared to just 10% in control areas, had free chlorine residuals between 0.2 and 2 milligrams per liter, indicating that they were applying chlorine correctly. This evaluation was made after the earthquake in January 2010, but focused on areas not affected by the quake. The Gadyen Dlo program was extended to the earthquake zone and accelerated greatly after the onset of cholera in the region in October 2010. 500,000 bottles of Gadyen Dlo were distributed in the affected areas for free. Use of Gadyen Dlo in the earthquake-affected zone has continued, but this may be due to continued distribution of free product. It's an open question whether people will be willing to pay for Gadyen Dlo once the free distribution period ends. While chlorine is by far the most commonly applied chemical disinfectant, there are other ones, especially in commercial treatment. Chloramines or chlorine dioxide are used in some cases, and ozone is gaining in popularity, but these are not typically applied at a household level in low or middle income countries. There are some emerging products which use bromine as an alternative to chlorine. Some filters have this. And silver has at least a bacteriostatic and maybe a bactericidal effect, and is often combined with another treatment, such as in ceramic filtration. So certainly one of the main advantages of chlorination is it's highly effective against bacteria, including cholera, and has been demonstrated to really stop cholera outbreaks. However, it's ineffective against at least some protozoa and requires longer contact times for viruses. Chlorine does give a residual protection which can help minimize recontamination or regrowth, but it has a characteristic taste and odor which people may find unpleasant if they're not accustomed to it. It's fairly simple to apply chlorine, but it does require that the water have low turbidity. Chlorine application is low cost, but does require supply chains to replace consumables. And then finally, there's often misunderstanding about disinfection byproducts and the relative importance of these, which can cause resistance to chlorination programs. So in summary, chlorine is a widely used disinfectant in both conventional treatment and household water treatment. Chlorine can be obtained from a wide variety of sources, but all of these produce free chlorine in water, which is the active disinfectant. Chlorine is highly effective against bacteria, including Vibrio cholera, and also is effective against viruses and some protozoa, but is not effective against Cryptosporidium, which is a major cause of disease. Cryptosporidium cysts are larger and should be removed through filtration processes, especially following coagulation and flocculation.